Cool. Thanks a lot for having me. Yeah, I'm Niklas, and I'll present Generative Representational Instruction Tuning, or GRIT. The motivation for this work is that there's two types of language models, really. One is embedding models. So given some text, they produce some numbers. And then you can use those numbers for a variety of use cases, such as clustering, where you then cluster different texts based on their numeric representations, semantic search or retrieval, text mining, and many other things. And there are many models for this, like from OpenAI, text embedding 3 large, BGE, E5, and many others. And the other key part of text-based language models are generative models. So given some input, their output is text. So not numbers, but text. Even though inside of the model it's also numbers, but they then get turned into text. And these are probably even more known, like GPT-4, Gemini, Llama, and many others. And they can then be used for generating stories, answering questions, chat, and many other things. So we have these two types of models, and they both power many use cases. And essentially every text-based language problem can be reduced into one of those areas. So either it's like a problem where you want like a numeric tensor, and then you use it for clustering or whatever, or your problem is something that requires text as output, if it's a text-based problem, and then it's like question answering or whatever. So given that we have these two areas, does it make sense to combine them such that we have one model that handles literally all text-based use cases of models? And there are three possible advantages from combining. One is we could imagine that once we combine them, we might get better performance, or at least very good performance on both of those directions, so on embedding benchmarks like MTAB and so on, and also on generative benchmarks. The other thing is that often these models are used together, and we might be able to have efficiency gains by combining them. So one example is RAG, where we use both embedding models and generative models together to generate some text based on some retrieved context. So retrieval-augmented generation, RAG. And can we speed this up if both of them are the same model? And the third possible advantage, or very likely advantage, is just simplicity. So many companies, for example, they serve endpoints for both embedding and generation. So OpenAI and others, they have separate endpoints for each. And that, of course, requires separate infrastructure to handle each of those use cases. And we might be able to make that much simpler by just having the same model under the hood. And so we unify representation and generation, or representation meaning embedding, essentially the same thing for this talk, and refer to this as GRIT. And the way it works is that we simply have our embedding or representational inputs, such as those depicted in blue here, and our generative inputs depicted in red, and we both feed them through the same model and distinguish them through instructions. So the instruction kind of tells the model what it has to do, and then from the model we either get an embedding, and we can use this for all the embedding tasks that we discussed, or for all of the generative, or we get a generation and use it for the generative tasks. And the instructions ideally should be very detailed. So for embedding instructions, ideally they contain domain, intent, and unit, so that the model can create a really good semantic representation. So this is the high-level view of how GRIT is supposed to work. In detail, there are some differences to handle both of those inputs and outputs. So first, we mentioned the instruction, which is slightly different, but then also the formatting is different. So we use a different format to represent the input if it's for embedding or if it's for generation. So we have this embed part in the blue box on the left-hand side for embedding, and then on the right-hand side, it's like this commonly seen assistant part. And then it can also be multiple turns where the user and the assistant, they kind of chat with each other. So this is all supported. And then the attention is also different. So for embedding, we use bidirectional attention, which is depicted by the blue boxes, which are fully connected. Whereas for generation on the right-hand side, there it's causal attention and only connected toward the right. And essentially for embedding, you get intuitively, it makes a lot more sense to use bidirectional attention because you can create a better representation this way, because now the early tokens, they can also see what's coming later and can sort of adjust their vector representation. And whereas if you do it causally, like in generation, then the early tokens, sort of the early part in the sequence, doesn't know at all what's coming after, and so the representation might not be as useful. But of course, for generation, you have to do it causally because you don't know what you're going to generate. So you do it causally for generation, but bidirectionally for embedding. And then for embedding, we do some pooling to get a fixed size vector out of this structure. And then for generation, there's like a language modeling head on top that converts the hidden states of the model back to words. So this is how they're treated slightly differently, but it's the same model, the same parameters, only like slight differences in treatments in order to accommodate the differences of representation and generation. And then the next thing we need to consider is combining the losses. So for embedding, when we fine-tune a model to be good at semantic embedding, we usually use this contrastive loss with hard negatives. So that's like, these are all very common formulas. I'm not going to go into detail here, but yeah, they're very interested in how they work behind the scenes. And on the right is the loss for next token prediction that's very commonly used, where the model just has to predict the tokens that come next. And so how do we combine them? We literally just go with, I think, the simplest thing that you can probably do. We just add them on top of each other, and we have like a weight in order to adjust which one is more important than the other. And so, of course, each of those is also computed on different samples. So we have like embedding samples that do the embedding part that we depicted in the slide before, and then the generative samples that go through the generative part, and then we compute the generative loss on them. And yeah, both of them combined then form the loss for GRIT. And so now that we've laid out the recipe, which is pretty simple and should be generalizable to many use cases, this is how we specifically construct our language models, GRITLM 7b and 8x7b. For embedding data, we use an extension of this E5 data set, which contains, it's essentially a collection of a bunch of embedding data sets like MS-Marco, Squad, and so on. And for generation, we use Tulu2, which is also a collection of a bunch of generative data sets, FLAN, Open Assistant, and so on. And we fine-tune a language model on both of them, combined with the loss that we saw earlier. And this then results in our GRITLM 7b model on the right-hand side. And the language model, in our case, we use Mistral simply because through some ablations that we have in one of the later slides, we found that that works best with those models. But you can also pretty much use any language model you want, even non-transformers. It should even work with non-transformers since the approach is largely agnostic of the architecture. So yeah, our models that we focus on are GRITLM 7b and 8x7b. So the 8x7b is a mixture of experts based on the Mixtral model. And that means that it has much more, so it's sparsely activated, but it has much more parameters, but it doesn't use all of them at each forward pass. And this is how the resulting models perform. So embedding performance and generative performance, we measure both. And among the models that we compare with, so we try to compare with pretty much the best models out there, we find that they either match or outperform them. So on embedding, the GRITLM 7b model, so this is the MTAP score, which is this master text embedding benchmark that's commonly used to benchmark embedding models. And with 66.8, it outperforms all other models that we have here. So like the OpenAI embeddings, Instructor, BG, and so on. However, we have to say that it's pretty large. So with 7 billion parameters, that's quite a lot for an embedding model. So that gives it a big advantage, but also makes it somewhat slow for embedding compared to some models that might have less parameters. And then on the right side, for generation, again, we find that the models are pretty good, and the GRITLM 8x7b, so the big, very big model, outperforms many models, even Llama 270b, even though it uses less parameters during each forward pass. So that's quite quite good performance. And of course, the most important part is that that's the same model. So we use the same model on the left side and on the right side, the GRITLM 7B and 8X7B. They're the same, and they can handle both of those use cases essentially at state-of-the-art performance. And if we don't do grit, so if we only do generative or only embedding, which are these gen-only and emp-only lines toward the bottom, then it only works for one or the other. So gen-only, for embedding, its performance is 41.2, which is pretty poor. Whereas for generation, it's kind of good. It's slightly worse than the GRITLM 7B, but almost there, pretty much the same. And then inversely, emp-only, it's really good for embedding, so it matches GRITLM with 66.8. But for generation, emp-only 7B doesn't work at all because like it completely changes the model, and with 7.6, it's essentially useless for any generative task. So GRITLM shows that we can combine both of those in one, and a better way to represent this is essentially this plot where we plot the embedding performance on the y-axis and the generative performance on the x-axis. And GRITLM is the only model really that can handle both at really good performance, whereas prior models, they have been in this sort of, we cluster them here in kind of embedding models and generative models, and you can't really use them for the other one at good performance. So for embedding models, one big problem is once you fine-tune them for embedding, you get rid of the language modeling head, right, that it uses from pre-training. And so if you want to use it for generation after, then if you can try to just put that back on. If it is a model like the SGPT one, for example, you can try that. But we did try that. It's in one of the scores, and it doesn't work at all. So that doesn't work. And then for generative models, if you want to use them for embedding, nonetheless, you can just extract their embedding. But yeah, as the performance shows, it doesn't really work well. You have to fine-tune them for good embedding performance. Cool. Any questions thus far? So I'll have a bunch of breaks to make sure that people can ask questions, but you can also interrupt me anytime if there's questions. Yeah, good point. So it's a supervised loss. So it's in this case, it's supervised. So the hard negatives, they're created by either you just hand label it and you have a data set where you have you have your base query, which is like some question, for example, and then you have a positive sample that ideally answers the question, and then a negative sample that is maybe very similar to the positive one, but sort of different in a slight way, and that makes it like really hard to distinguish and makes it a hard negative. And yeah, those are, so in our case, they're all supervised data sets like these. Yeah. Yeah. For all of it. And the way sort of this loss works intuitively is that it pushes the query and the positive sample closer together in the Latin space, and then it pushes the representation of the hard negative really far away, forces the model to make it very different. Yeah. 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 So I think for one of the OpenAI models, originally what they did is they constructed unsupervised embedding data sets, and they used like just literally, I think, web pages, and then samples sort of text next to each other is sort of positive, and text that's very far away is negative. But I think it didn't work that well. I know. Yeah, yeah. So it's interesting because in Vision they use kind of essentially the same formula for some of the embedding tasks there. Yeah, a lot of parallels. Yeah, sorry, it's a lot of numbers for a slide. Um, yeah, that's a great point. So it doesn't seem like there's a major benefit from including both. It matches. Yeah. Yeah. I have many more slides. But maybe one more point I wanted to make here is, in addition to the hard negatives, there's also in-batch negatives. So we also contrasted from all the other samples in the batch. And that's why the contrastive loss, it's always important to have a big batch size so that you have more negatives. Yeah. Cool. And yeah, and yeah, one more point here. So the Gen-only 7B and the GRITLM 7B, they're the same. They're based off the same Mistral 7B model. So that's why, yeah. So this is like the main comparison. And of course, ATIC 7B, that's much bigger, has more parameters. So that one is expected to be much better than the Gen-only and the 7B one. Yeah. Of course. Yeah, we'll go into that one now. Yeah, great question to go into the next section. So RAG with grit. If there's anything else, yeah, feel free to interrupt. But otherwise, let's move on to this one. So the other benefit that we expect is efficiency. So RAG, retrieval-augmented generation, is the setup where we use both an embedding model and a generative model, and they work together. So for example, we have some query from the user depicted here at the bottom, how to prevent aging, or any question that the user might have. And then we use an embedding model to represent this question. And with an index, we compare this embedding with an index. And the index essentially contains a lot of documents that we have embedded previously, like prior to starting this generation process, and sort of cached. And then we find the best match. So based on embedding similarity search, we find the best match in the index with this query. So that might look something like this one here. So this is our document that we get from the index based on the similarity matching. And then we feed them to the generative model. So both the query and this document that we got from the index, and then the generative model generates a nice answer for us and sort of tells us how we can fix this or how we can do whatever our question is. And what immediately stands out is that this is kind of inefficient. So we have to feed this question to the embedding model first. And then later on, we have to again feed it through the generative model. And same with the corpus. So this document here, we feed it through the generative model. And of course, to construct the index prior to running this part depicted here, when we construct the index, we also need to feed every document in the index through our embedding model once and encode it in order to get this vector database, which is our index with all the embeddings. So essentially, we have to pass each of these twice through two different models if we have a separate generative and embedding model. But now that we have this grit language model and the generative model is the same as the embedding model, we can make this process much more efficient. So the first technique that we introduce is query caching, where we simply reuse the query representation for retrieval. So it could look like this, where we feed the query or the question into our model, but in this case, it's not a generative and not an embedding model, but a grit model, grit language model. and then we reuse the hidden states that this model produces for this query and use them to find the document in the index that matches it. And then we feed this document also through GRITLM, so just like here through the generative model, but we don't have to feed in the query anymore because we can just reuse the previous pass that we did on the query. In practice, we just reuse key value caches. So key value caches are like these, is a part of the model that essentially, so the key value states is essentially what's used for the attention process. That's what the model attends to when it looks at the past. And so if we just cache them here and then reuse them, we don't have to feed this input to the model again, but we can just plug in those caches and it gets much faster because we only have to pass through this new input essentially. And then, yeah, we get our generation. So here, our speed up is essentially equivalent to one forward pass over the query. So we expect query caching to be really useful if we have a very long query, because then this one here is going to be very slow because we have to pass this very long query twice, once through the embedding model and once through the generative model, whereas GRITLM should save 50%, so we only have to pass it once through the same model, and then we reuse the cache. We can go even further and do query doc caching, where we cache both. So here again, we pass the query through the model, and then so at inference, like a user comes in and he has some question, we feed that through the model, and then compare it with all the documents in the index that we created ahead of inference. So that's usually just done previously and cached. And then when we get this document back from the index, instead of getting back the text, we just get back the cache of the document itself. So when we create the index, we also store all the caches of each document in this index. And we don't need to store the text anymore because we don't care about the text, we just care about the caches. And so then we just give the cache back to the model, we concatenate this document cache with the previous query cache, and we generate. So now we save inference equivalent to both a pass over the query and a pass over the document, because the pass over the document is only done to create the index, and we don't have to do it at inference anymore. And so this is query doc caching. Of course, we can also do just doc caching, so we can also only cache the documents, so we have them in the index and only cache them, and still feed the query through both the model to embed it and for generation. So we can do various combinations here. And query doc just means that in the prompt, so we also distinguish between query doc and doc query, and the difference between query doc and doc query is just the position of the text in the prompt. So query doc means we feed the query first in the prompt, and doc query means that the doc comes first. So when we generate later, we need to concatenate these two caches, and either we put the query first or the document. So this is the intuition, and now we're going to look at how this works. So first, we're going to look at the problem of this setup. There's two problems. One is that, as we discussed previously, we use bidirectional attention for embedding and causal attention for generation. So that means that once we concatenate these caches, and if we reuse the model, then inevitably there's going to be an attention mismatch where so part of it is bidirectionally attended and part of it is causally attended. So there's two ways. Either it's as depicted here, so we have the embedding text, which is here in blue, and that's used to embed it. So that's bidirectional. Every blue box is connected with each other. And then we use that as the cache, and the model sort of causally, with the red blocks, generates from this bidirectional cache. And then, of course, when it does this causal generation, it's going to be a bit confused because the caches are not similar to what it has seen during its generative training previously, because suddenly they have bidirectionally attended to each other, so they might be a bit corrupted, a bit unexpected. And the other case would be, we can, of course, just not use bidirectional attention and just use causal attention for embedding. So we, instead of having bidirectional attention for embedding, we use causal attention for embedding. So all boxes would be red in this case. But then the problem is that the embedding performance is going to be slightly worse because the bidirectional one performs better. So there's one trade-off: either we trade off kind of the generative performance or the embedding performance. And we will see how this works out. And then the second problem at the bottom is that so this only applies to if we cache both the query and the document. Then the problem is that we're combining separately attended texts. So what this means is if we cache both, then we first embed the query and cache it. And then we get so in the slide that we saw previously, we get the cache from the index. So the document has been embedded and we get the cache from there. And of course, this document has been embedded without any awareness of the query. It doesn't know what the query is going to be because we embedded it previously to construct the index. And so then when we do inference and we concatenate these two caches, then they haven't attended to each other. And so this is also very different from what the model has seen during training, where the subsequent texts always have seen the previous text. And here, essentially, we're going to have these 4 boxes in the middle, and they have no awareness whatsoever of the stuff that happened previously. So the caches again are going to be slightly corrupted, and then that might reduce performance. But we're going to try it anyways, and we'll see how bad it gets. And yeah, again, this is only for caching both. So we can, if we only cache one or the other, then we only have to deal with the first problem. And if we cache both query and document, then we have to deal with both problems 1 and 2. So how bad is it? So here we depict the performance on like a simple retrieval-augmented generation tasks. We use natural questions where the model is asked some question, and then the corpus is based off of Wikipedia, and we retrieve some document that's close to the query from the Wikipedia corpus, and then try to answer the question based on that. So the baseline at the top is just not using RAG at all. So we don't use the Wikipedia corpus. We just try to answer the question directly with our GRITLM 7B model. So this is all GRITLM 7B. And we find that the correct answer is 21% of times. The correct answer is in the generation of the model. And so now we get to the various RAG and caching variants in the lower half. First, it might help to take a quick look at the prompt on the left side. So for query caching, the prompt looks something like this. So we have so not depicted in the prompt is what's cached. So the document is cached. And then the user, for example, asks some question, what is grit? And then we tell the model to answer this query with using the context that has been cached prior to it, and then it generates its answer. And then for doc caching, it's the other way around. The document comes first in the context, and then the query is cached, and then we put the document in the context, and the model answers it. So then on the right side, let's look at the performance on the match performance. So just using RAG without any caching leads to 30.5 match, so better than no RAG. So this just confirms that our corpus is actually useful. Now, if we use query caching, then the performance drops by 5 points to 25.46. So this is likely because of the first problem that we discussed here. Yeah, that kind of hurts. And then if we use query doc caching, so we cache both the query and the document, it gets even worse. It drops by 9 points. Yeah, so this problem here, this is probably because this problem here is pretty bad. So this makes the performance almost reduces it back to not using RAG. However, it saves us a lot of inference time. It gets much faster at the cost of reducing performance. And then for doc caching, it roughly matches RAG, so that's pretty good. However, if we do doc query caching, so again, caching both, then it gets much worse. So overall, query doc caching and doc query caching are not really worth it, but doc caching and query caching can be pretty useful. Doc caching is usually seems to be slightly better. And now we're going to look at some latency. So how does this change the speed? So if we scale the query length, so at the bottom is the query length as we go from the left to the right is the query length and tokens. And as the query length increases, then of course caching it is more and more, improves speed more and more. So while no retrieval and traditional RAG, they just explode at some point and seconds per example. So the inference speed, inference time it takes to process the example goes up massively. If we cache the query, so the blue line, then it stays roughly at the same level. And similarly, if we use any of the combined caching techniques, it also it doesn't explode and it's very cheap to do inference. However, of course, these two, query doc caching and doc query caching, don't work that well, so we might not want to use them, but query caching can still be pretty useful. And now if we scale document length, so this is more common. It's more common that the documents are very long and the queries are kind of short because it's just a question. Then then doc caching is kind of the best we can do. So the yellow line that's kind of in the back here, it sort of stays toward the bottom as document length increases, while traditional RAG, so just not doing any caching, but still retrieving a document, eventually explodes in inference time. And here, no retrieval also stays at the bottom because, of course, if we don't do retrieval, if we don't do a RAG, then there is no document. So increasing the document doesn't change anything really. So doc caching can be really useful. So that's probably the most useful of those caching methods because usually documents are pretty long. It didn't really impact performance. If we go back here, performance was roughly the same or even slightly better. And it can massively save inference time. All right, any questions at this point? Otherwise, we're going to go into ablations. Mm-hmm. A good point. So in this case, since the GRITLM model it's only a decoder, so we don't have an encoder. But I guess what you mean is like as the answer gets longer, does it still save time? I think so. Since at every point of generation, at every point where you generate a token, you still use the like the next new token. You look at the entire background, at the entire cache. So like there might be some. Yeah, but then that's cache. Yeah, I don't think it really helps. Yeah. So if you only generate one or two tokens versus hundreds of tokens, it doesn't impact it. Yeah. So I think it only saves equivalent to the document time. How much you decode doesn't matter. Yeah. Yeah. So I guess that could be a drawdown if your answer is very long, the relative savings aren't that big anymore. Yeah. Yeah. Yeah, I think the most common one is probably having like huge documents, and then short queries and relatively like mid-sized answers, I guess. No, so we could run the 8x7b model, but then that would be bigger. Though it's also not much bigger. So since it's an MOE, it only uses I think 14 billion parameters at inference, or 13 or something. So it's not like not going to be an order of magnitude. Yeah. Yeah. So I think probably for bigger models, it would be even more important to cache because, of course, it's more expensive. And then in the traditional setup, there's also considerations of the size of your generative model versus embedding model. So if they're different models, then one might be small, one might be big. So it's very common to have very small embedding models. So then the speed up might not be as big. Yeah. Cool. Yeah, feel free to interrupt if there's anything. Otherwise, we'll go into ablations. So the first ablation that we looked into is attention and pooling. So if you recall, in the final model, we decided to use a bidirectional attention for all the embedding part and causal attention for the entire generative part. And so we ablate whether that's the right choice. So first, let's look at embedding only. So here we just train pure embedding models. I'm not doing generative fine-tuning. And there we find that so either we do causal, so everything is causally attended, or we do causal plus bidirectional, so causal over the instruction, which comes at the beginning, and then bidirectional over the sample that comes after, and then just doing fully bidirectional, which is our final model, and the fully bidirectional one performs best. The pooling also slightly changes. So for fully bidirectional, we use pure mean pooling. So this just means that we average the representations of every token. So we just take the mean. And weighted mean pooling, or W mean here at the top, has been shown to be slightly better for causal models. And it's very similar, but it just gives later tokens a higher weight in the mean, like in the averaging. And this makes sense because, of course, later tokens in a causal setup, they've seen more of the sequence, whereas earlier tokens, they haven't seen as much, so they have kind of less information. But yeah, doing bidirectional with mean pooling gives us the best embedding performance. So emp here refers to the embedding performance. It's just the emtab average. And then gen is just the average across our generative tasks. And for these, it doesn't matter because this is embedding only. Now we're gonna look at generative only. So what's the best attention setup there? And of course, there's no pooling for generative. It's just the language modeling head on top. And we find that a causal, like fully causal, gives us the best performance. We also tried bidirectional plus causal, so we can do bidirectional over the instruction. And then the sample always has to be causal because it's what the model generates, right? So it doesn't know what it's going to generate in the future. So it has to be like in this causal setup. But we did not find that doing bidirectional over the instruction improves performance, which is odd because some prior work did find that it improves performance. So yeah, it might come down to implementation details or how many fine-tuning steps you do. But yeah, so we stick with only causal. And then our unified model, or unified GRITLM model, we then go with this setup of bidirectional plus causal. We still also run the other ones to make sure that it's also best in the unified setup. But overall, we found that the ablations on only embedding or only generative, they largely also also hold for the unified setup. So yeah, bidirectional plus causal with mean pooling is the best here, and also confirms that the performance more or less matches. So here we even got a slight improvement on embedding compared to the embedding only variants. So the unified one is at 64, while the embedding only one is at 61.8. However, these ablations were run on a different data set, and then once we switched to the E5 data set that we used for the final model, we did not see this difference anymore. Yeah. So the next ablation we run is the base model. So we tried the Mistral, which we also used for the final ones, Mistral 7B, and also Mixtral 8X7B. And we also applied Llama 2 and GPT-J. And we find that fine-tuning, when we fine-tune all of them with Grit, then Mistral is by far the strongest. And what's surprising here is that if we don't fine-tune them, then the GPT-J model was actually the strongest for embedding. So just after pre-training, prior to doing any Grit fine-tuning whatsoever, GPT-J has the best performance on MTab with 45.2. And then Mistral, and then Llama. However, after fine-tuning, the Mistral model was better. So it's interesting because it tells us that kind of the embedding performance just after pre-training is not predictive of the embedding performance after fine-tuning for these causal language models. The next ablation is the base data set. So for on the embedding side, we iterated through MEDI 2 and E5. So MEDI comes from instructor, which is a prior embedding model that sort of introduced the notion of instruction fine-tuning for embedding models. And that one gave us a performance of 64. And then we created our own version of that, MEDI2, essentially also created by the same person. And that was slightly better. But we got the best performance by using this E5 data set, which gave a pretty big boost. And this data set contains a lot of samples that were generated by GPT-4 and ChatGPT, which is interesting because it's synthetic. So these are all synthetic samples, but apparently they're really good and can be better than the other samples that you can get from public data sets. However, E5 still contains non-synthetic samples, so just a part of it is generated by GPT-4. And on the generative side, on the right side, we found that the Tulu-2 dataset gave us the best generative performance. UltraChat was also not bad, and OASIS-T was a bit worse. And Tulu-2 contains many instruction data sets, so that might be one reason. Like, it has a pretty good diversity, and that could be part of the reason it performs this well. But then also the Tulu-2 dataset, the paper that introduced this work, they use the same generative evaluation as we. So we took the generative evaluation setup from their amazing work. So it could be that they kind of tuned their data set for precisely these generative tasks. But these are pretty common generative tasks like MMLU, GSM8K, so everyone kind of uses them. So yeah, I'm not sure, but it is definitely a pretty good data set. Yeah, and then the next ablation is the embedding head. So one big consideration with embedding models is how big is their dimension, the dimension of their vector representations. The bigger it is, the more expensive to cache it, because yeah, if you cache it, then that literally increases the file size, and so you need more space to cache it if it has a bigger representation. So we experiment with down projecting it with a linear head. So that's depicted here at the bottom. So we just get our representation from GRITLM, which has 4096 dimensions. So that's the hidden dimension of the Mistral 7B model. And then we put a linear layer on top that we also fine-tune during the GRITLM, the grid process. And it down projects it to 1024. So a 4x reduction, which also means saving 4 times the money in terms of storage. And we found that it does perform pretty similarly. So this downscaling to 1024 doesn't hurt performance as much, but it still slightly hurts performance for embedding, and oddly also for generative, even though it doesn't impact the generative part at all. But yeah, since it's the same model, even if we modify only kind of one side of it, it also sort of affects the other one. So yeah, also a slight reduction on generative. And thus we decided not to use this for the final model, but it might make sense for certain use cases where the storage is really limited. This might be useful. So this model is also released. We pretty much all of the models from all the ablations, they're also all open source. So if someone thinks that this model makes more sense for their use case, they can of course just download that one. And the next ablation is batch size. So as we briefly touched on earlier, the batch size is really important for embedding because of this loss formulation where we essentially have all the batch samples. So the batch size corresponds to M in this formula, and all the other samples, they're contrasted against each other. So that we call this in-batch negatives. And so the in-batch negatives increase, of course, if you increase the batch size. And that means that we get a better, the loss becomes more exact because we get more samples to contrast each sample with. And so sort of it gets a better position in this latent space. And yeah, so as expected, increasing the embedding batch size, so BSM from 256 to 4096, improves embedding performance, and generative performance in this case doesn't really change. because also we don't change the generative performance here. Yeah. So for the final model, we use 2048 actually, so slightly lower, mainly because it's very expensive to use such a big batch size. So 4096 is pretty huge. And the main problem with using such a big batch size is the memory constraints. So it's difficult to, so there's some techniques for reducing the memory, and we detail all of our techniques in the paper. But nonetheless, it is difficult because, yeah, you need to, in the worst case, you need to hold each sample in memory, and they can be pretty huge. And then in our case, since it's also both embedding and generation, we might even have more things in memory from the generative part. So we have some techniques for reducing this. One is grad cache, which stems from prior work, where they show that you can do some caching, and you don't need to, it's sort of like gradient accumulation for embeddings. That's one that works pretty well. We also developed this technique of splitting the embedding of the query and the document. So not embedding all of them together, but splitting them, and also splitting the backward pass, both of which are detailed in the paper. But yeah, so because it's pretty expensive for the final model, we only do 2048. And actually for the GRITLM 8x7b, we go even lower. With the embedding batch size, we only do 256. So this is the 7B model. And then for the 8x7b, the MOE model, we do 256 embedding batch size, which could be the reason why it performs slightly worse on embedding than the 7B. So we saw that earlier, like its generative performance is much, much better. Its embedding performance is slightly worse than the 7B model. And that's probably because we reduced the batch size. Yeah, but even with this reduction, it was still fairly expensive to run, but it would be worth it probably trying to scale it up at some point and do a bigger batch size for that one as well. Great. The next ablation is precision. So we ablate using FP32 or float precision 32, which is also referred to as full precision with bfloat 16. The advantage here of using bfloat 16 is that it's cheaper usually, so it only uses half the, in a certain sense, half the precision, even though it's not quite like FP16, but half the precision. And so that means it could be twice as fast, and also at inference it might be faster because we don't have as many numbers that we need to store or need to compute with. And we find that it doesn't hurt performance. In fact, it even slightly improves performance using BF16 here. So on embedding, it stays roughly the same. On generative, it slightly improves, or FP32 is slightly worse. For the embedding part, there's still some things that are in FP32. So essentially what happens is after we get the representation from the model, then we cast it back to full precision. So we cast it to float 32, and then the pooling, so the mean pooling is done in float 32, and then also the similarity computation with cosine similarity is also in float 32. So that means that if you want to cache the representations after the pooling and then reuse them at inference, this is not equivalent to this BF16 setup, but we do have another ablation in the paper where we simulate sort of casting them back to BF16, storing them such that the storage is cheaper because it's half the precision, and then casting them back to FP32 for cosine similarity once you load them. And that's slightly worse than what we do here, but it's still good enough that it's worth it for most use cases, I think. Yeah, and there are also some other things that are in FP32, like Torch has some things that are always in FP32, and so on. Mainly, I think, layer norms and some other operations. Cool, and the next ablation, so I'm just running through ablations here, but if anyone has a question, feel free to interrupt. Yeah, not many ablations left. One more is in-batch negatives. So here we benchmark whether it's best if the negatives that we just discussed, so in this embedding formula, we have those negatives that come from the other samples and also the hard negatives. But here it's only about the negatives that come from the other samples. If it's best if they come from the same data set as the sample we're looking at right now, or if they can just come from any data set, it doesn't matter. The intuition is that if they come from the same data set, then they might be more useful. They might be more similar to hard negatives because now they're the topic is very similar, so it might be really hard for the model to distinguish them, and sort of might lead to better representations, because now the model has to distinguish them based on really, really tiny differences. But in practice, the embedding performance stayed roughly the same. However, we do notice a massive boost on retrieval. So retrieval is one of the embedding tasks that constitutes this 66.0 average score. And for that one, we got a pretty big boost. So we did use it for the final model, because retrieval is one of the most common use cases of vector embeddings. So that's why we went with this. And also the generative performance oddly slightly improved, even though it doesn't really impact the generative loss or the generative part at all, except for because it's the same model. Cool. And then another ablation we ran is the formatting. So we distinguished the 202 and the Zephyr beta format. For Zephyr, they used an additional, it's essentially the same, except for the additional end of sequence token after the user utterance that they use in Zephyr. And we found that this leads to slightly worse performance, because it makes the model finish its generations earlier. So it's sort of like, when the end of sequence token is generated by the model, then that's usually when we finish the generation. And so if the assistant generates this end of sequence token very early, then sort of it doesn't have as much space to say what it thinks or give its response. And we find that if this end of sequence token is also in the user utterance, so the user, so sort of what we prompt the model with, and we put the end of sequence token in there as well, and then let the model generate, then this leads to shorter generations of the model itself, possibly because it sort of already has this token in its context, and then it's like, oh, I'm going to generate it again a bit earlier. And yeah, that's why this worsens performance, and so we just go with the 202 format. And then the final ablation I'm going to discuss is loss. So in the formula earlier, that's depicted here at the bottom, we have the final loss of grid is just the sum of the representation loss and the generative loss, and each of them can be adjusted with a weight, lambda rep or lambda gen here. And we play a bit with those weights and mainly measure the loss ratio of the representation loss to the generative loss at the first step. So what this means is that if the ratio is very high, so the representation loss is much higher than the generative loss, then the model is then most of the optimization is going toward optimizing the representation objective, right? Whereas if the generative loss is much higher, and so this ratio that's kind of the second column here is low, then the generation loss gets more weight and the optimization is more focused on that one. Intuitively, we want to have a bigger representation loss because that loss is completely new for these models, whereas they've already seen the generative loss during pre-training. So there's probably not as much work to be done there, but probably they have to really learn how to represent stuff. So that's why we make sure that it's bigger than 1. So the ratio is bigger than 1. So the representation loss is bigger than the generative loss. And specifically, yeah, we find that going from 2.4 to 6.0 improves performance. So especially on an embedding, well, though even on generation, surprisingly, but also on embedding. So because it has more weight now for its representation or embedding tasks. And then we find that we get the best performance here at the bottom with a ratio of 4.1 and the type being a mix. So what this refers to is, okay, I see we're out of time, but I can still go through this one, I think. So the mix means that we have a mix of token loss and sample loss. What token loss refers to is that each token gets the same weight, whereas sample loss refers to that every sample gets the same weight. And the difference between token and sample is just that a sample would be, for example, a summarization sample. So we ask the model, please summarize this text for me, and then the summary is sort of what the model is trained on. And if this entire thing gets the same weight as another sample, and that sample might be question answering or something else, then that's what we refer to as sample loss. And token loss is if we just give each token the same weight, regardless of what sample it belongs to. And so intuitively, if we use token loss, then samples that have lots of tokens, like generating a very long story or maybe also summarization, they get a lot of weight, whereas short samples which is just like a question with a one token answer or one word answer or something, they don't get a lot of weight. And so it's kind of a trade-off. Like, do you want to give more weight to those longer things or not? Or do you want to give each sample the same weight? And we find that mixing them, so we go from token to sample loss, gives us the best performance. So what this means here is we do 32, we do token loss for 32, so token loss across 32 samples. And then we do sample loss after that, sort of where we kind of aggregate them all and then do sample loss. It's detailed. There are more details in the paper about how this works. But yeah, it's just that combining them gave us the best performance. And there's some considerations, with which one you use. It changes how the model generates text, and especially the length of the text that the model is going to generate. Cool. Thanks a lot. And yeah, feel free to ask any questions if there's anything else. If you want to learn more, the papers on arXiv, everything is open source on GitHub, pretty much everything. Unfortunately, we couldn't open source the E5 dataset, but otherwise everything is open source, either on GitHub or Hugging Face. And yeah, feel free to reach out or ask any other questions. Of course. Yeah, good point. I'm pretty convinced they were. So with regard to seeds, we always use the same seeds. So that shouldn't have been a confounder. And then also the average. So even though it's just emb or gen here, but actually there's tons of tasks behind the scenes. So emb is all of mtep, which is 56 different data sets that are measured. And then generative is also a bunch of tasks. So the average should be pretty solid. So yeah. I see. Yeah. Yeah. Yeah, this is all the Mistral 7B. Or generative. So the generative average actually also contains one multilingual task, tidy QA. So there's some multilingual in there, but yeah. Not hearing it. Yeah, I haven't. So it hasn't been too long since we released it, so I haven't heard many things yet. But one thing I've heard, or one additional problem, is that I think the caching part is what's really attractive. So it's also without the caching, it's kind of attractive because it's essentially a state-of-the-art model. But then for embedding, even though it has the best performance among like fully open models with a commercial license, it's pretty big. So actually, we can take a quick look at this. Is like the MTEB leaderboard that I think is commonly used. So other models usually they're much smaller. So they're like 1.1 or 1.3 gigabytes. So that makes it pretty expensive, even though it is the best open one. So this one here is an API, and this one is non-commercially licensed. So it's the best for like commercial use cases. That's open source, openly available. But yeah, like it's pretty big, so it's still pretty expensive to run. Yeah, and then one problem I wanted to mention that I've heard is that often in those RAG use cases, people want to have multiple documents. So not just one document, but you want to provide it multiple documents in the context. And then again, we run into the second problem here, because now they're all encoded. They have all been embedded separately. And then if we concat them, then they haven't seen each other's cache. So I think it might not work that well with multiple documents. Yeah. 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 You could still do query caching. Great point. And then one thing, so my intuition is that if you fine tune a bit with this, because the model has never seen this, I think that's the main problem. If you would fine tune a bit and sort of let the model know that this is going to happen and it's going to have a mesh, then it might not be an issue anymore. Yeah. I think it should be pretty simple and it should work. I haven't had the time to do it yet, but if someone's interested, feel free to reach out. I'm happy to. Yeah, I think it could be pretty impactful. So one thing I did try is doing preference training on top of the model. So I'm going to put out the results somewhere soon, but essentially just doing, so we did KTO, which is this alignment method, on top of the GRITLM model, and we found that it works pretty well. So generative performance improves further. And even though in this KTO phase, we don't do any embedding training anymore, the embedding performance still stays pretty strong. Okay, great. Cool. Thanks so much for having me. It was a lot of fun. All right, thank you.